Thank you again to everybody who's joining us or has just joined us for this evening's She Talks Science webinar from Murray Edwards College at the University of Cambridge. My name is Matt and I'm part of the team at Murray Edwards College. It's my pleasure to have you all with us this evening for a really exciting talk that we've been looking forward to. In a moment, I'll hand over to our speaker, Professor Hiranya Peiris, who is a cosmologist that studies the universe. She holds the 1909 Professorship of Astrophysics at the Institute of Astronomy at the University of Cambridge, and she's Professorial Fellow in Astrophysics at Murray Edwards College here at the University of Cambridge. During the talk, the Q&A session will be running, but just so we're clear, we're not going to stop and take questions during the talk, so please do make sure that any questions that come to mind as we go are written in a way that still makes sense when Hiranya finishes her talk, and she will spend a few minutes doing a brief Q&A session going back through. If there are any questions that come up that aren't to do with the talk, I will be there throughout, so I may well answer some questions for you. But otherwise, when we get to the end of the presentation, Hiranya will look through and spend some time answering your questions. So please do share if things come to mind. That is everything from me to get us started. So it's my very great pleasure to hand over to you now, Hiranya.
Can you hear me?
Absolutely.
Okay, let's get started. I'm going to share my screen. How's that?
Good to go.
Good to go. Okay. So it's my great pleasure to talk to you this evening about decoding the cosmos. So in the last 25 years, we've pieced together a model of the universe that describes its origin and its evolution. This was an audacious undertaking, and you won't be surprised to hear that we haven't quite cracked the cosmic code yet. Just by looking up at the sky at the largest scale that we can see, we've uncovered deep holes in our understanding of fundamental physics at the smaller scale. And to solve this cosmic mystery, we need to look at the puzzle from many different viewpoints. And to do that, we are building a multifaceted toolbox that combines data from huge new astronomical observatories with the latest advances in AI techniques and complementary information from laboratory experiments. So in the next hour or so, I'm going to show you some of the latest developments that I'm personally most excited about. So to start with the most basic point, what makes cosmology possible is the fact that light has a speed limit. It's very fast, but it's finite. Because light takes time to travel to us, even from the nearest stars, we see those stars as they were in the past. So observing the distant universe is a kind of time travel. As we look out into the depths of space, we see the universe as it was in the past. And this allows us to see how the universe has evolved over time and to compare what we see in the sky with our cosmological theory. You can roll back time in this way to the oldest light we can see in the universe, which came into being 13.8 billion years ago. And we call this the cosmic microwave background. So the map that you can see in this picture was a milestone measurement of the cosmic microwave background, which shows a baby picture of the universe when it was only 380,000 years old. You know, that might sound very old to you, but it's currently, remember, 13.8 billion years old. So this is a baby picture. This picture was made by Planck, a European Space Agency satellite. And Planck brought the early universe into sharp focus and measured the parameters of the cosmological model with pinpoint precision. An example is the age of the universe, a question asked by humans since the beginning of history, measured with 0.5% precision. So we can't do experiments with the universe, so I want to give you a flavor of how we use maps like this to learn about the universe. In addition to maps of the sky that we measure, we also have theories that make predictions for what the sky should look like. We can calculate predictions for what universes built using different physical cosmological models look like, and we can compare those predictions with the data. So this map is like a fingerprint, and you can identify the right theory by comparing a lot of theories with the data and coming up with the one that fits the fingerprint. And in that process, we can also eliminate a lot of theories whose predictions don't match the data. And when we do that, we find something rather surprising. All the information in the millions of pixels in the map is well described by only 6 numbers. And these 6 numbers tell us the shape, the age, and the clumpiness of the universe, its constituent components, so atoms, dark matter, dark energy, and when the first stars formed. So the model of the universe that describes the data seems surprisingly simple. But this simple model contains 3 ingredients that are not in the standard model of particle physics. There's dark matter and dark energy, and the early universe was clumpy. So what made all of that structure in the beginning of time? So those 3 ingredients are not in our standard theories of physics. The universe is simple, and yet it's very strange. So while we measure these parameters very precisely now, the standard cosmological model remains phenomenological. What is the physical nature of dark matter and dark energy? We don't know the answer to those questions yet. They together comprise 95% of the energy budget of the universe. The matter made of atoms like stars, planets, people, you and me, everything tangible to us in this world is only 5%. We also don't know where did all the stuff in the universe come from. So the leading hypothesis is that a tiny instant after the beginning of the universe, a so-called scalar field, a quantum field, which we call the inflaton, caused the universe to rapidly expand by a factor of at least 10 to the power 26. We call this process inflation. This is not what's happening to the economy right now, it's what the universe did back at the beginning of time. At the same time, tiny quantum ripples in this field got stretched out by the expansion of the universe to become the seeds of all the structure we see in the universe today. And then 380,000 years later, you see the imprint of these ripples in the cosmic microwave background. These little ripples in the distribution of matter in the universe then grows under the structure and under the action of gravity to form all the complicated structures we see in the universe today, 13.8 billion years later. So the starting point of my talk is that the study of the oldest light we can see in the universe revealed a simple but very mysterious universe. And in the rest of my talk, I'm going to give you a flavor of the new tools that we can leverage to crack this cosmic code. The first approach I'm going to show you is mapping dark matter with a billion galaxies. So it's worth remembering that it was only about 100 years ago that we discovered that there were galaxies other than our own Milky Way. So in October 1923, the US astronomer Edwin Hubble identified the first Cepheid variable star in the Andromeda galaxy. That's the nearest large galaxy to the Milky Way. We know that now, but that was the first time we proved that the galaxy was not part of the Milky Way. So why was it so hard to work this out? It turns out that measuring distances in an expanding universe is very difficult. Hubble used an ingenious approach involved with a class of pulsating stars called Cepheid variables. This method had been worked out by Henrietta Swan-Leavitt in 1912. This is still one of the most accurate ways we have to measure cosmic distances, but it only works in our cosmic backyard, as it were, because these stars are not bright enough to see far out in the very distant universe. So we'll shortly see that working out how far away galaxies are is still a key challenge in using them as cosmological probes. An obvious way to view the universe is in visible light. There's a reason that our eyes have evolved to see the universe in optical wavelengths, right? The sun has significant radiation output at those wavelengths. So starting in the 1990s, we've been mapping the universe in starlight in very deep and large-scale galaxy surveys. So what you see in this movie here is part of the so-called Sloan Digital Sky Survey. This is not a simulation. Each one of these galaxies is a real object. There are about 400,000 galaxies in this movie. For me, the Sloan Digital Sky Survey represents the point that the field of cosmology became a data-driven subject. The full size of this 20-year survey was not huge by modern standards. It can be stored in about 40 terabytes. Even an individual researcher these days can aspire to that much storage. So it's not that much these days. But this was a watershed moment for the automated acquisition of digital survey data from the sky. So when we map galaxies using light, we see them arranged in this intricate cosmic web. It's because these galaxies are tracing huge filaments of dark matter that you can't actually see. You can't see 80% of the matter in this image. This is a slide through a simulation of how galaxies trace dark matter. So now you're seeing a simulation of the formation of a cluster of galaxies. Cosmological simulations are a key tool in understanding what our sky surveys are showing us. Using computer simulations, we can make detailed predictions for the fingerprint of different cosmological models, which will alter how galaxies are scattered in this scaffolding of dark matter. And we can compare those predictions with the data and figure out which of these theories match the data and which don't. So our understanding of how galaxies populate the universe is about to be revolutionized due to major facilities that are about to come online. And cosmologists are gearing up for the torrent of data that's about to come upon us. We are truly in the era of big tech and big data. And to make sense of that data, we need big algorithms. The project that I'm personally most excited about myself is the Vera C. Rubin Observatory's Legacy Survey of Space and Time, or LSST. LSST is the ultimate big data project. It's starting operations in about a year's time. And the pictures of the universe we've obtained to date are mostly static. They're frozen in time. Instead, Rubin will return to every part of the southern sky, roughly every 3 days or so, and do that for 10 whole years. And so by stitching those images together, we'll make a movie of the dynamic universe. And this will enable us to study space and time in a way that's never been done before at this scale, and expand the surveyed space-time volume by a factor of about 1,000. So as a comparison, I previously mentioned the Sloan Digital Sky Survey as a milestone in this field. A single sky scan from LSST, one of the pictures that it takes every 3 days, will be as deep as the entire Sloan Digital Sky Survey over its 20 years of operation. The Vera C. Rubin Observatory is named after the pioneering astronomer who established convincing observational evidence from galaxy rotation curves about the existence of dark matter. So this is the first major astronomical facility named after a female scientist. I think it's about time. This amazing purpose-built survey facility is now taking shape on the summit of Cerro Patron in Chile, where the skies are perfect for observing deep into space. So LSSD will enable diverse science missions at the same time. In addition to investigating the nature of dark matter and dark energy, it will make an inventory of the solar system. It will look for those near-Earth asteroids that might collide and threaten the Earth in the future. It will make this movie of the universe that I described, and it will make a detailed map of the Milky Way galaxy, thereby enabling even more tests of dark matter. And the resulting data set will contain 60 petabytes of raw data, 500 petabytes of processed data. It is truly big data in terms of its volume, its rate of delivery, and its variety. This picture is showing where the camera will be mounted. It is the largest digital camera ever constructed. It is the size of a car, and it will observe the sky in huge 3.2 gigapixel images. Each image will be 3.5 square degrees. That's about 40 times the size of the full moon on the sky. The camera has just this month arrived at the summit for installation. It was taken from where it was constructed in California. It was flown there, and then it was driven up to the mountain. And it has apparently arrived safely. So that was really cool. This huge structure is so perfectly balanced that you can move it around apparently with your hand without using force. So I was incredibly lucky to be able to visit the Rubin construction project last December. I joined this project in 2013, and it was truly incredible to see how the engineering drawings we saw back then have become a reality. And now we have to be prepared for data next year. So one of the most powerful ways that we can leverage this huge galaxy catalog is to map dark matter with what's called gravitational lensing. So in Einstein's theory of gravity, mass bends light. This image shows how dark matter in a massive cluster of galaxies in the foreground is lensing distant galaxies. This leads to this exuberant display of multiple images and arcs that you can see in this image. So I'm going to illustrate this with a video of a demonstration. Okay, so I'm going to play the video now, and you can see this lens. It's not a typical lens. This lens is shaped like the gravitational potential of a galaxy. So you can now see how this lens is being moved across a grid, and staring down the barrel of the lens, it is, lensing that grid very heavily. But what we care about is what's happening in the outskirts of that image. So now let's traverse this lens across a image of galaxies. And if you look at the corners rather than right at the center, you can see that the pictures of the galaxies in the corners is being slightly distorted. So photons travel towards us from distant galaxies. Their paths get very slightly bent by dark, massive structures that they have encountered on the way. These structures form part of the cosmic web. So this effect is called weak gravitational lensing. Weak lensing of galaxies by intervening dark matter distorts their shape and position very, very slightly. The amount of distortion is related to the distance light has traveled. By measuring the distortions, you can map out the dark matter over the history of the universe. So you can now hopefully appreciate that if you don't have an accurate estimate of how far away the galaxies are, you will not measure the amount of distortion along the line of sight, and therefore the amount of intervening mass accurately. This means that you get a distorted picture of where the matter is in the universe and how it evolves under gravity. This means you'll draw wrong cosmological conclusions. So we don't want that. So we want to solve the problem of how far away galaxies are. So A really good way to find this out is by measuring redshift, which I'm going to illustrate to you now. So I'm sure you've seen many rainbows lately, given all the wet weather we've been having. So in this picture is a wonderful example I photographed a few years ago in Iceland. So here, water droplets in the air are splitting sunlight apart into its constituent colors, which are characterized by different wavelengths. So this graph illustrates how the light from the sun is distributed as a function of wavelength. This is called a spectrum. You can see bluer colors are at shorter wavelengths, and redder colors are associated with longer wavelengths. So now let's think about the spectrum of an incandescent light bulb. If you look at a light bulb through a diffraction filter, you can break its light apart. And so what can you see in this picture? When we break it light apart, we can see a rainbow, right? So it's a rainbow, but it's got greater emphasis on the reds than the blues compared to the spectrum of the sun. So that was an incandescent bulb. What about if we go and look at a hydrogen bulb? Why hydrogen? Well, hydrogen is the most common element in the universe. In fact, most of the atoms in the universe are hydrogen atoms. Most of the rest is helium. And astronomers call all the other leftover elements of the periodic table metal. They only comprise a couple of percent of atoms in the universe by mass. So it's mostly hydrogen. Galaxies contain hydrogen, so maybe we want to look at the light of hydrogen. And so what I'm going to show you next is the light from heated hydrogen. And again, we view it through a diffraction filter to break it apart. So this is what you see if you do that. So this is not a rainbow, right? You can see three lines here. There's a very bright red one, a fairly bright blue one. And if you can look very, very carefully, you might see a faint violet one, okay? So now if we go to the spectrum picture, hopefully we're not going to expect a rainbow, but something different. We're going to expect three lines at three different wavelengths. And ta-da, that's what you see, okay? So you see three lines on the spectrum. They are blue, violet, and red. And these particular spectral lines of the hydrogen atoms are the so-called Balmer series of quantum mechanical transition in the hydrogen atom. So spectral lines like this are crucial to measuring redshift. So in the laboratory on Earth, we know what wavelength the spectral line should be at. This is fully determined by quantum mechanics. When we observe the same lines in galaxies further and further away from us, we see these lines shifted to longer and longer wavelengths. So shifted to redder and redder colors, because the wavelength of the light is being stretched out by the expansion of the universe. It's becoming longer and therefore redder. So by comparing the measured wavelength of the light from the galaxy to its reference wavelength in the lab, we can work out how far away something is. So done and dusted, right? Can we go and take spectra of 1 billion galaxies and measure their spectral lines? Unfortunately, the answer is no, not with current detectors and current technological capabilities. We can't get a spectrum of every galaxy in the LSST galaxy catalog. So instead, Rubin will measure 6 colors per galaxy, not the full spectrum. So we have to work out the redshift from these 6 colors without access to the individual line. And to be able to do that, we need to understand how colors of galaxies connect to their physical characteristics. So in the past few years, this key realization has dawned. To decode the cosmos, we need to understand galaxies. And this is a challenge because galaxies are complicated beasts, and understanding their light distribution is related to their constituent population of stars and the gas and dust they contain. So now imagine that you have a recipe for generating realistic examples of galaxy spectra and colors. What ingredients would that recipe contain? So the light that galaxies emit depend on their properties like their mass, their star formation history, their dust, their gas, their metallicity. So there is such a recipe that allows you to predict colors of galaxies. It's known as stellar population synthesis. And we can leverage this tool to solve this challenge. So the key idea is that you can work out how far away galaxies are if we solved another more general problem, which is to be able to faithfully model the diversity of galaxy properties in the universe over cosmic time simultaneously with the redshift. So this problem is not tractable with traditional approaches when you consider current catalog of hundreds of millions of galaxies, let alone LSST's billion galaxy sample. However, modern machine learning models can accurately describe the complicated web of interdependencies between these different galaxy properties. These tools have only become available very recently in the last few years. Essentially, they turned up over the pandemic. So we have just succeeded in the first attempt at doing this, where the recipe for making realistic galaxy populations is encoded within an AI technology called a diffusion model. This is essentially a flexible mesh. It lives in 16 dimensions, describing ingredients in the galaxy recipe. So I can't personally imagine 16 dimensions. I doubt that you can either. So I'm illustrating the process of fitting a complicated model like this in 2 dimensions. So I'm now going to play an animation of this. So first, we make a realization of the data by drawing mock galaxies from this 16-dimensional model. And then we can compute the observable properties of each galaxy, for example, its colors. And then we can add noise and selection properties appropriate to a calibration survey. In this work, the calibration survey actually provides you 26 colors per galaxy. And so we can take these point clouds from the model and this 16-dimensional data space and minimize a metric between them. This metric is called the optimal transport distance. So at the end of the training, you get a diffusion model where if you draw from this model, it represents populations of galaxies in the real universe. Because the fitted model lives in the space of galaxy properties, it's independent of the calibration survey to which it was fitted, and can be used to predict galaxy colors for any other survey, including LSST. So we're very happy about this new tool. With tools like this at the ready, we can look forward now to when LSST starts next year. Here you can see a preview of a typical patch of sky seen by the Sloan Digital Sky Survey, and a preview of how much more detail will be revealed by LSST when it comes online. So in 100 years, we'll have gone from knowing one external galaxy exists to measuring a billion galaxies. Powerful machine learning technologies have become available just in time to do some heavy lifting here. And these tools help us to embrace the complexity and the size of the data set instead of fighting against it. And we can use these tools to help us decode the cosmos. Now I want to switch to a complementary approach to decoding the cosmos. And this part is about detecting dark matter in the lab. So a key unanswered question in cosmology is, what is a dark matter particle? There have been many creative theoretical proposals, as you can see in this figure, but there are two broad candidate theories: weakly interacting massive particles, so-called WIMPs, and axions. These are particularly attractive because they solve major problems in particle physics, in addition to providing compelling dark matter candidates. In other words, they haven't been invented to be dark matter. They have other motivations that are very powerful. So much of the experimental effort in the past decade has focused on the WIMP hypothesis. This is mainly for sociological reasons, I think, but also because the experimental technology was easier and more well developed. So it's only more recently that experimental attention is turning to axion. So there's a huge part of the axion parameter space that is relatively unexplored. So the QCD axion, so-called, is my favorite dark matter candidate. So the QCD axion is a compelling candidate because it wasn't invented, as I said, to just be a dark matter candidate, but rather to solve mysteries related to the standard model of particle physics, specifically something called the strong CP problem. So just to try to simplify, the standard model for particle physics has the neutron electric dipole moment as a free parameter, right? It can take any value. But when measured, it's very, very small, 10 to the minus 10. It is very fine-tuned, or it appears very fine-tuned. And physicists just hate fine-tuning. So the axion was proposed as a dynamical way to explain this fine-tuning. It was meant to wash away the problems of the standard model of particle physics. It's actually named after a detergent. You can see a picture of the detergent box there. So this type of dark matter behaves as a wave as well as a particle. Its wave-like properties are related to its mass. So how can we detect these types of particles? The axion has a very weak coupling to photons, which are particles of light. We could wait for several times the age of the universe for an individual axion to decay into 2 photons. Or if you're very impatient, which I am, we need to try something else. We could pump many photons into a very strong magnetic field to induce the decay. We need many, many axions in a given volume so that there's a reasonable likelihood of observing a decay into photons. When the decay happens, we get a teeny tiny electric current, which we can read out. So finding the axion is then a bit like tuning a radio. So the wavelength of the axion needs to match the wavelength of the photon to get the conversion. And this induces the electric current. Even with a 10 Tesla magnet, which is a very strong magnet, this is still a teeny tiny electric field that's induced. So when the size of the cavity matches the axion wavelength, we see a peak in the electric power. So higher and higher frequencies probe larger and larger masses. But this is inversely linked to the volume. At some point, the volume is too small to contain enough axion to generate a signal, and then you can't probe higher masses. This is the prime range, unfortunately, for where we expect the QCD axion to be. So how can we get around this? Ideally, you want to break the relationship between wavelength and frequency to allow you to keep the effective wavelength the same size as the cavity, but to probe higher frequencies and hence higher masses. So the key idea here is to give the photon an effective mass by using an effective medium called a metamaterial. A metamaterial is a designer material that allows you to control the relationship between wavelength and frequency. So you can change the effective mass of the photon to obtain the resonance, rather than changing the size of the cavity for zero photon mass. So that's the key idea. So if you only have the geometry of a single cavity to work with, that's like a radio where you're only allowed to scan over a very, very small frequency window, whereas the axion may be hiding in a mass range that is many orders of magnitude wide. So this is a big problem for traditional cavity experiments. They can drill down in a very narrow frequency window, but leave wide swathes of the candidate mass at other frequencies unexplored. But by using a wire metamaterial, we can also enable tuning because we can change the effective photon wavelength by changing, for instance, the spacing between the wires, as is shown in this movie. So here's another tuning idea. This is through the rotation of shaped wires called sails. These tuning possibilities mean that we can scan across a range of axion masses with one experiment, rather than being limited to a single narrow mass range. So we are currently experimenting with different wire metamaterial resonator prototypes. This is a PhD student at Berkeley, Heather Jackson, with a prototype that they're building in Berkeley. And here's a colleague in Stockholm, Jon Gudmundsson, in the lab, working with the postdoc Gagandeep Singh on a different prototype design. Notice that these are truly tabletop experiments. The magic facility is also the size of a university lab. This is in contrast to the truly gargantuan particle physics experiments that one typically encounters. So an experiment of this type, which we call ALPHA, is currently under construction at Yale University and will take data for 5 years. Cambridge University is a founding partner of this experiment as well. This will allow us to probe the most compelling mass range for the QCD axion. So the next few years will be very exciting for axion dark matter. In the last few minutes, I want to go back to the beginning of the universe. I want to show you a truly mind-blowing implication of this theory of inflation, which is the prevailing paradigm for the origin of structure in the universe. If this is a correct description of nature, inflation doesn't just make the observable universe. It makes a big universe, much, much bigger than that. Even more bizarrely, it will create structure on huge scales compared to the observable universe. It will create other universes, bubble universes, with our universe being just one among innumerable others. So in this picture, most of space on scale much larger than the size of the observable universe is trapped at high vacuum energy. What does that mean? So imagine being in a landscape of potential energy, like this picture of the terrestrial Taina range in Chile. You can tell I've been to Chile lately. So if you're at the top of a mountain, you have high potential energy. So a position of high vacuum energy in the landscape. So at that point, space is expanding at an accelerated rate. It is inflating. But you can end inflation by tunneling to a lower vacuum energy, like the lake in the picture here. This is called a phase transition, and it happens via the nucleation of a bubble of lower vacuum energy. This could have been the birth event of our own universe. However, the main hurdle standing in the way of even testing these ideas in principle is that our understanding of the relevant theory is just not good enough. These are really difficult calculations. It's as if the universe took all the hardest math that are needed to describe nature, bundled them all into one problem, and then told physicists, go ahead and solve that. So there are many assumptions and approximations involved, and we don't know which one of these are justified and which are not. So a new approach we are taking to understand the theory better is to emulate the same physical equation, but translate it within an experiment in the laboratory. So by comparing our maths with the experiment, we can refine our theoretical understanding. So basically, the idea is that you have a system you can't experiment with, in this case, the very early universe, but there's another system that you can experiment with, which under the right conditions exhibits the same phenomenology described by the same physics as the original system. If you can work out what those right conditions are for the physics to match, you can translate the understanding gained in the laboratory to the system that you can't experiment with, which is the very early universe in this case. So we're currently building in Cambridge a prototype in the lab, which behaves like a quantum field undergoing vacuum decay in the early universe. The experiment involves macroscopic collections of ultra-cold atoms called Bose-Einstein condensates. They operate just above absolute zero. Our laboratory universe, which looks very messy, will soon be transported into the science cell that's indicated in the picture, where data taking can begin. So I want to show you a system undergoing a phase transition, which also has a non-trivial link to the physics of the early universe. This system is not as strict math as the one that we're building in the lab, but it hopefully helps you get the idea. So in this system, this is a Tibetan singing bowl. Okay, so I'm going to now play the movie. The friction of the mallet on the singing bowl induces a resonance, which if you played with one of these, you can hear as a single note. When you fill the bowl with water, the resonance frequency of the bowl changes a bit, but there's still a resonance. And at the resonance frequency, the surface of the water is excited by the resonance phenomenon to make first waves that crash into each other, and then to start fizzing with bubbles. Isn't that super cool? I love watching this. You can recreate this at home if you get hold of a Tibetan singing bowl or a metal bowl like this. So you're probably familiar with another phase transition of water when you boil it to make your morning cup of tea. That's a phase transition that also happens through the nucleation of bubbles of steam in liquid water. But there, you explicitly inject energy to make that happen, right? You heated it. Here, the phase transition is happening simply because of the resonance, which causes the system to have a large response to a small periodic variation, which is rubbing it with the mouth. On one hand, it's just a Tibetan singing bowl. On the other, the surface of the water behaves like a 2+1 spacetime, undergoing so-called particle production that is thought to have happened in the early universe in a process called parametric resonance. So that is hopefully a nice demonstration that illustrates this concept. So this is a fairly unique collaboration at the intersection of condensed matter experiment and cosmology theory. Even just thinking deeply about this problem before we have any data in the laboratory to compare with has led to advances in the understanding of the theory beyond the standard approaches that were available up until now. I can't show you yet analog bubble universes nucleating in the lab, but what I can show you are computer simulations of what the bubbles would look like in an experiment versus our best understanding of what happens in the very early universe. By tuning the experiment in different ways, and by turning the analogous knobs in our mathematical calculation, we can see whether our expectations are correct. For example, for the rate at which bubbles nucleate, and how that depends on different physical properties, or what is the likelihood of one bubble nucleating right next to another one that's already formed. Through experiments like this, we hope to better understand the very, very extreme conditions in the very early universe. So we've come to the end of our time. I want to end by emphasizing that understanding our universe required interlinked progress along many frontiers. The field is currently being driven by technological innovation, which is producing huge volumes of very complicated data, which we need to model accurately, to interpret it, and to contextualize it in terms of fundamental theory. And I hope I've managed to convey an impression of how the interplay between theory, observation, and experiment plays out, and hopefully motivated some of you to join us in this quest to decode the cosmos. Thank you very much. That's the end of my talk. And I will look at the Q&A now.
Thanks so much, Hiranya. Even I understood much of that, which is quite a feat for a non-physicist. There are a couple of questions come up already. I think actually Alexander's question, he asked before you got to that part and then very comprehensively answered it, but there may still be something there.
Okay. Now I'm very happy to answer these.
Marvelous,
so,
thank
okay,
you.
The first one says, what does intensity represent in the intensity wavelength graph? So that is the amount of flux energy, light energy that actually you receive from that wavelength. Okay, so if you see a higher intensity, you'll probably see that color as brighter. There's a more technical definition of that, but it's basically that kind of qualitative sense. So you probably saw in the case where there were three spectral lines, one was higher in intensity than the other, the red one, and you saw that red as brighter when you saw the picture of it. So that's kind of the relationship. So the second question is, what in your opinion is the best way to study dark matter, and how close are we to discovering what it's actually made of? Thanks. Okay, good. So I think I showed you one way that I think is really excellent to look at dark matter in the lab. And I showed you another way to study the behavior of dark matter in the context of the universe by studying weak gravitational lensing. So those two, I think, are very good ways to approach the problem. The issue is that the theories have been very, very creative. And so there are many different conceptualizations of what is the dark matter particle. In my opinion, the key ones to look at are these two kinds of dark matter, WIMPs and axions, that have a motivation other than simply being a dark matter candidate. So those are the two I would focus on. And the reason that I think axions are particularly interesting is that the WIMP parameter space has been very thoroughly searched already with huge experimental effort. And we are very close to actually closing that off. So if you have two classes theories and they're equally well motivated and you tested one, I think you should start by testing the other. So that's why I personally work on the axiom. Okay, so there's another question, which is what wavelength of the EM spectrum is the most interesting to observe the universe with? I would say all of them. Okay, so I told you a couple. I showed you the cosmic microwave background. You see this in the microwave. So by looking at the microwave, the light from the early universe has shifted so far into the red, it's actually getting close to radio frequencies, right? So that's in the millimeter wave. Okay, so basically that shows you the very early universe. Looking at optical wavelength shows you lots of light from galaxies. Galaxies are the key components that we study in the universe as a whole. And so that's a good wavelength range to look at. You can look in the radio as well, and you can see interesting processes going on in galaxies in the radio. And you can look at very high energies as well, X-rays and gamma rays. Astronomers study the universe with all of the available wavelengths really in the EM spectrum. And on top of that, I didn't get a chance to talk about this. We also study the universe now using gravitational waves, which is not electromagnetic radiation at all. It is the vibrations in the space-time that we can detect with incredibly exquisitely precise instruments here on Earth, and also by using rotating neutron cells, pulsars, as clocks. So yeah, we have many ways to look at the universe now. New windows are opening up all the time. It's a very exciting field. Now we have what would solving issues with the standard models such as the distribution. Okay, keep jumping, sorry. What would solving issues with the standard models such as the distribution of matter to antimatter help astrophysicists better understand the universe and how? Yes, absolutely. So a standard model is something which represents our current best understanding of how the universe works, right? So the standard model of particle physics tells you about the behavior of particles and fields and forces in the universe. But the standard model of particle physics only describes the 5% of the universe made of atoms. The rest, the 95%, we don't have a fundamental description of. So if we understand that better, we understand fundamental physics better. It's a huge hole in our understanding of physics. And so that's the reason that we are trying to better understand the properties of the standard model of cosmology. Could you re-explain how you're trying to replicate early universe scenarios at Cambridge? I'm going to leave that one for you to re-watch in the video because I don't think I can repeat that part right now. There's another question. Why do we need a 16-dimensional model to describe galaxies? So the 16 dimensions is what it happens to need to describe the complex spectra of galaxies well. It just happened to be that number. There's nothing special about that number. And that is the number of ingredients that we need to model galaxies with. And as I mentioned, these are ingredients such as the mass of galaxies, their star formation history, whether they have active galactic nuclei in them, heating them up, what is the gas content, what is the dust content, things like the amount of metals in the gas, things like that, and the ages of their stellar populations that relate to their star formation history. So it just happened to be 16. There's nothing particularly fundamental about that, and we can increase that number with the methods that we have if we think that more complexity is needed. They're coming in thick and fast. Let's see, with the expanse of the universe and the many variables involved, how do you make sense of all the data that you collect from your research? It's by this tight connection between fundamental theory, going to modeling observables, and then to comparing the observables that we modeled with the data through principled statistical models. That's the process that we use in our field. And yes, it sounds very complicated, but when you break it down into these kind of individually understandable pieces, you can put it all together and read a narrative of the universe that makes sense in the light of all the observations we've made to date. So hopefully that is clear. Another question, do you think the field will continue to develop at the same rapid pace it's done during the past century, or will things begin to slow down? I don't think it is slowing down at the moment. We are opening so many different new windows into how we can observe the universe. You know, less than 10 years ago, we started observing the universe in gravitational waves. We currently have huge sky surveys operating across all of the wavelength regimes I talked about. And when we gather all this data, we are going to open up new questions. That's what happened 20 years ago when we put together the standard model of cosmology. And we found that 95% of the universe was not described by the standard model of particle physics. So we have opened up huge theoretical questions, and we are gathering enormous volumes of data to answer them. So I think the pace of discovery will only accelerate. What could have triggered inflation? Could the rate of expansion... Okay, I can't quite understand the question, but what could have triggered inflation? It is literally this idea that I try to explain, where you start out at a position with high vacuum energy, and most of the universe outside our observable horizon is still doing that. So if it starts somewhere, it's just going to continue eternally, and it will only stop locally, and it will only stop by the nucleation of a bubble of lower vacuum energy, and that represents the birth of our own universe. So so that's the idea. What happened before inflation? We have no idea. So this is how far we have currently pushed back our understanding of the universe to an instant after the beginning of time. We don't know what happened before that. How does gravitational lensing work if dark matter does not interact with light like normal matter? Okay, so dark matter is just mass. It doesn't need to interact with light like normal matter. It will just bend light. Okay, it's just like any mass bends light. Dark matter also bends light because it has mass, and therefore there's a gravitational effect that perturbs space-time around a huge bunch of dark matter, and that bends light. Okay, sorry, I didn't finish my previous question. Why would the rate of expansion change, and is high vacuum nucleation still observed on a large scale? I don't quite understand the question, but if you're referring to the bubble nucleation thing I was talking about, when you're at the top of the hill, the space where the potential is at the top of the hill expands at an accelerated rate. And once you've tunneled down to the bottom of the hill, to the lake, it is expanding still, but it's expanding at a non-accelerated rate. So it's merely the change in potential energy that has caused that phase transition. Okay, I think what makes an axion different from other particles in the standard model? So the axion is not part of the standard model. It is there to explain curious observed fine-tuning about the standard model of particle physics, which is called the strong CP problem. And I explained it in terms of fine-tuning of this particular parameter, the neutron electric dipole moment, which is observed to be 10 to the minus 10 when it can take any value. So it's an extra mechanism outside the standard model of particle physics. And if we actually detect the axion, it will extend the standard model of particle physics. Hopefully that's clear. Okay, let's just see. If our universe is four-dimensional, how exactly do you have 26-dimensional data? Aha, that's a slight confusion, sorry. The data is not it's not 26 spatial dimensions. It's just a data cube, which is 26-dimensional, and each dimension is a color. Okay, I'm not talking about space there. I'm talking about a 26-dimensional data cube. And I was able to show how we fit the model in 2 dimensions. Now imagine that process happening in 26 dimensions. That's what I meant. Hopefully that's clear. And I will perhaps take one last question. I think I've answered everything else. How did you decide that this field in astrophysics was the one you were most passionate about? I wanted to learn about the universe ever since I was a kid. I was one of those people, and I think that I like it because it asks the biggest questions that there are in the universe. We're trying to understand the whole universe, and I think that the grandeur and the just the immensity of it really appeals to me, and I think that it's one of those fields in which you can follow your curiosity in many, many different ways. You don't have to do the same as what everybody else is doing, and you can find your own path. And there are many questions to ask and many questions to answer. And another reason is because, as hopefully I try to illustrate, you get to work with fantastic people, and you get to collaborate with them and share knowledge, and work with people all over the world to answer these questions. So I think that's going to be the last one I take up. And so thanks very much. I think that was quite a lot.
Hiranya, thank you again so much. And thank you to everybody for joining us this evening and for so many fascinating questions. If you are interested in engaging with us directly at Murray Edwards, you can contact us at outreach@murrayedwards.cam, that's cam.ac.uk. And that is our outreach email address. If you have questions that you'd like us to pass on to Hiranya after the talk, we can package those up and email Hiranya on your behalf. Or if there are questions about anything else that goes on at Murray Edwards College or the wider university, we can come back to you via that email address as well. But thank you again to everyone for joining us this evening, and a very big thank you, Hiranya, for your time and for your fantastic presentation this evening. So thank you very much, everyone, indeed. And that brings us to a close. Enjoy the rest of your evening, and hopefully see some of you soon at Murray Edwards. Goodbye.
Goodbye. Thank you so much.